Okay, let's get started. So you can hear me, right? Yeah. Okay. So they're going to be about, I believe, 50 students in the class, 51, 52 or something, about 50 students in the class. And and I think it's like a large number is MS. After MS, there is a large number from computer science, a smaller number from robotics automation, about 7 or so from PhD, and a few bachelors, like a couple of bachelors. And I think this is approximately going to be around until people. I think the ad drop is over as far as I'm concerned. So there may still be changes, but that's approximately like this. Okay. Why is this? Okay, so I also kind of forgot to mention last time, I guess, but it came probably clear when I signed in the Piazza. There are like 4 people still who supposedly are in the class who haven't activated their Piazza account, unless they're planning to drop. If you haven't activated your Piazza account, and you're not seeing what's going on in the Piazza, you're missing what's happening in the class in general. Also, I think I asked people to do mandatory exercise, and there only about 35 people did it. That's not the definition of mandatory. That basically means that you're actually going to fail the class if you keep doing that sort of thing. Okay, so basically keep track of what's going on the Piazza. And you can also ask questions there, and I do actually look at that. And then, like I said, there is no special book. There's no book that you need to buy for the class. I'm going to kind of take pieces from different freely available books from the library. These are all basically, these are all the synthesis lectures. And so that's like a faster thing to read. I mean, there is actually bigger books on each topic, but I think that this is good enough as far as this class is concerned. Plus, as I said, part of what I'm sort of planning to do is combine planning in these ways versus planning with LLMs. So kind of we'll interleave them. And for the LLMs with planning, there's no actual textbooks. We'll be reading papers. Okay. So that's where you will be reading papers and reviewing them, etc. So that's approximately the thing. And I hope you all recognized. I mean, I will start caring about actually testing whether people read things or not from next class. But for today, I will basically hope that people opened the concise introduction to planning and looked at the first 2 chapters as much as you can, because I think I will still be looking at it today, but you're supposed to, yes.
I just want to share my thoughts about the chapter thing.
1 second. Yeah. So that's basically the required reading essentially. And I think we'll be going forward. Approximately, I will, cover some of that stuff in today's class anyway. So that's the case. And then, so today, what I'm approximately planning to do is essentially kind of complete some of the discussion, the introductory discussion that we ran out of time last time. So I'm going to quickly go over that and then get into, I mean, these things will be combined because the first chapter of the readings essentially would be what is planning, et cetera, et cetera. So you can combine those pieces. Okay. So that's what I'm planning to do. And so anyway, this week's talking about planning, validity, optimality, robustness. You should be able to understand the distinctions. And they'll wind up what is a valid plan for classical domains is different from what's a valid plan for probabilistic domains, because in the case of probabilistic domain, you can only talk about the probability that the plan will work, because it's never going to be guaranteed 1.0 that the plan will work. So that's the other thing you see. And optimality is and we talked about robustness is in essence, if in fact the model is incomplete. All our models of the world are always incomplete, and they might actually be incorrect too. And so in particular, if a model is incomplete, one way of thinking about it is this incomplete model is consistent with some huge number of complete models, one of which happens to be the real world. You understand what I'm saying? So there's an incomplete model that corresponds to many, many real potential completions, one of which happens to the real world. And so what you are saying is, if the plan is working in this incomplete model, what you really want to have an assessment of is what is the fraction of these completions is it likely to be correct? If you actually know which is the real world, that's easier. Okay, but on the other hand, since you don't know what the real world is, and you have some ignorance about the real world, basically you have to look at the fraction of the models of the world in which this particular plan is likely to work. And so that would be the robustness. Okay. And in general, this sort of a thing becomes quite interesting in the context of reinforcement learning, where you combine planning and learning the model. One way of understanding reinforcement learning is that it combines the learning of the model in terms of reinforcement learning. Again, by the way, I sort of assume that you have heard some of these topics beforehand, introduction to AI, etc. So I'll kind of be saying it as if you know partially some of these things. If not, you need to kind of either stop me or also, if you haven't actually taken intro to AI at all, you have to pick up things. Okay. So in the case of reinforcement learning, what happens is that essentially we will wind up learning these transition models, action transition models, saying if you do this action in this state, what are the possible states you can potentially get into? And then this transition model and the reward model, that is what states have what kind of rewards for the agent. These are not known to the agent beforehand. If it is completely known, then reinforcement learning is a classical planning problem. It's like a standard planning problem. You understand what I'm saying? And the reason reinforcement learning is kind of interesting is that you're sort of learning the model as well as planning with that model. And when you are doing that, it becomes clear that a plan that is greedily optimal with respect to the current incomplete plan may actually be pretty inoptimal with respect to the rest of the model that you don't know of because you haven't yet learned it. Do you see what I'm saying? This is where these things like robustness come into play. What is basically an agent supposed to do? Is it supposed to optimize the reward with respect to its current incomplete model? Or should it also spend some of its time exploring the rest of the world to increase, its knowledge about the rest of the world? And if it's not doing any exploration, then the robustness would be, if this is the incomplete model, what are the possible complete models that are consistent with it? And in what fraction of those models would my plan be correct? That's what will be robustness. Okay. And then generally planning assumes the model and dynamics of the world. And of course, that you know what the goals are and the goals have to be specified. And typically goals may be specified in the classical planning case, the kind of stuff that we'll start with. You will specifically say what your goals are. But then as you go forward, you will notice that sometimes goals will be given, some goals will be given, and there's a large number of common sense constraints would not be specified. Do you see what I'm saying? And assuming that everybody knows that those constraints are actually part of the specification. And this is one of the cases where actually like being able to take the goals plus the implicit common sense constraints and making sure that the plan is correct with respect to both of them is going to be important. And that's one of the few places where actually LLMs have an edge because they have approximately the common sense that might be present in all the stuff that we have written on the web. Whereas a classical planner, for example, just knows what you have said. Do you see what I'm saying? Okay. Then of course, the models of planning depend to some extent on whether it's a domain-independent planning. So domain-independent planning essentially looks like this. Planner, domain, initial state, goal state. Domain-independent planning takes as input the domain, the model. Do you understand what I'm saying? If, on the other hand, if you have a domain-specific planner, domain-specific planner just says, don't tell me the domain, I know the domain. Okay, I just know one domain, and that's the domain I'll assume you are looking for. Just tell me your initial state and test. That will be the domain-specific planner. Do you guys understand this? Okay. And then goal specific planner says, don't even give me the initial state. Don't even give me the goal state. Just give me the initial state. You understand what I'm saying? Just give me the initial state. Okay. Interestingly, the stuff that you're going to be looking at that you already read about, where basically the domain independent planner, you will give the block solid domain in PDDL, and then you will give the initial state in PDDL specification, and you'll give the goal state and say, this is what the goal I want, and then it needs to figure out how to generate the plan. Okay, if it is domains, basically the advantage of domain independent planner is to some extent you have to understand that if you're taking the input, that means you should be able to take any kind of input. If you change the domain, you can take that as input. If that input is not being taken, in this case, that means it's been compiled in. So there's only one specific domain for which it will work. Right? And then you come here, it only works for one specific goal. Here is a very interesting thing. Classical reinforcement learning is this. Because normally classical reinforcement learning assumes there is a single reward function. A single reward function corresponds to a single goal, essentially. Do you understand what I'm saying? So if you want to write, just a second. So if you want to write like block solved problems in reinforcement as a reinforcement learning thing, then anytime the block solved problem goal changes, you need to change the reward function. Do you see what I'm saying? And so it's kind of important to understand these distinctions because people talk past each other, doing this and comparing to this, without realizing, that we are talking apples and oranges comparison is not going to be helpful. You see what I'm saying? If you are here, you should be actually talking about, can I take any arbitrary reward function? Right? And one of the things that happens because of this, it turns out that, okay, once in a while, tell me you guys, by the way, that once in a while, if I'm waiting for like 45 minutes before changing the slide, which I hope will never again happen because it happened last time, please remind me because apparently Zoom will stop recording. But anyway, so one of the interesting things that the word generalization is a very fraught word. Everybody says it generalizes. What the heck do you mean by generalizes? Okay, and the word generalization is kind of related in the machine learning terminology to in versus out of distribution. In versus out of distribution. So you trained it on certain kinds of problems, and if you are asking it to solve problems that humans might think are similar, but they're actually not in the, not strictly in the distribution of the problems you train them on, will it be able to solve it? This is something that keeps coming up when you talk about LLM reasoning and planning. Everybody wants to make claims saying it generalizes. But what does it generalizes mean? Generalization here would mean, for example, things like, can you actually generalize if you know how to solve one IG, kind of one class of IG, can you do different kinds of initial and goal state configurations? If you know how to solve blocks world, can you solve a new kind of blocks world, for example, where a single block, some of the blocks can take 2 blocks on top of each other. Some can only take 1 block on top of each other. That's a kind of generalization. You see what I'm saying? Generalization in this case is, since you are assuming that the domain is the same, you can't even say you can change the domain. Right? You're mostly going to be asking, can you potentially take different IGs? And generalization in this case is even worse, essentially, because, at best you can say, if I change the reward function, can you still live? Do you understand what I'm saying? Again, I'm bringing this up, I have this, what's his name? It's Schopenhauer or somebody who said that life only makes sense when viewed backwards, but unfortunately you have to leave it forwards. Courses also are the same way. The entire course will make sense at the end of the time, and when the course is over, lots and lots of these points will make sense later on. But I have to say it upfront. When I'm saying it upfront, you're not yet ready. You're not started thinking about generalization. So, but you have to kind of hold this for like a whole semester, and that will really help quite significantly. Anyway, so that's very important to understand that the reason we're thinking about domain independent, domain specific planning algorithms is it's connected to these notions of what it means to talk about generalization. Okay, and you have to ask yourself when somebody says I'm doing planning, you have to ask yourself, is this or this or this? Okay. And then, of course, if the models are being learned, then the models can be learned. The models can be learned from the agent's own experience, which is strict RL, okay, and are from other people's experience, which is LLMs. Right? The problem with other people's experience is that they are, first of all, the thing about LLMs essentially is, to the extent they can understand, you can actually capture the world model, the people who wrote the language experience, if you can actually extract it from the language, even if you assume that is the case, it's still going to be the issue as to whether people are truthful in writing there what they actually have seen. On the web, there is no notion of truthfulness. People will write whatever it is that they want. And so, in essence, you're trying to get some sort of a notion of model of the world from those things. And if you want truth, assuming that it's not unwashed web, you can consider traces, trajectories experienced by other agents. So you basically ask, okay, tell me what happened in your life. You did this, you did this, you did this, and you write it down. Sometimes you might be dying. And then basically I just get to still see it. As you're dying, you write it down and you die, and then I use that as my training. Remember the Grand Canyon example, right? So the interesting thing is, if you are learning from other people's experiences, that's different from learning from your own experience. And one of the issues really is, if you're learning from other people's experiences, you may or may not be able to go beyond their collective experience, because you never did anything that other people haven't yet done. Okay, this is going to be a big issue, as I think I mentioned it last time too, that with the case of LLMs, you can think of it as this notion of humanity's knowledge closure. If you take up the entire humanity and they wrote everything that happened to them, that's approximately you can think of that's what as the web. Okay, LLMs are sort of trying to train themselves on that. There is incorrectness within that knowledge, I understand. But the question is, can they actually go beyond humanity's knowledge closure? And that basically will require actually doing work in the world. Okay, one of the weirdo things that happens in my life of late, because we are in AI, is I have no idea whether I'm teaching classes or I'm teaching New York Times reporters. I actually described this whole thing yesterday morning, to a New York Times reporter, because they were very interested in companies that talk about recursive self-improvement. If you can have AI improve itself, it's done, right? Everything AGI is tomorrow, right? Now, what stops it from happening? In fact, already one of the nice things you have to understand is, first of all, I said, papers, you should be skeptical. Companies, you should be skeptical too. Nobody ever says the whole point of startups is fake it until you make it. Right. Sometimes, like this poor woman of Theranos, you get caught while you are in the middle of still faking it before you made it. If you made it before they caught on, they will never put you in jail. That's the interesting part. Every damn company has to fake it, because the investors want to hear more than what is actually possible right now. So if you look at any random thing saying Google says or startup X says, put its capital Q. Okay, so anyway, there are only two companies which are for recursive self-improvement stuff. And this report I was asking, do you think this is all possible? And the answer is essentially it depends on do they have their own experience or not. And do they have, for them to have their experience, this whole discussion that I did last class matters. You can say I can have an experience by doing that requires doing actions in the world. And when you do the actions in the world, and if the world is not benign, then the actions that you do can get you into trouble. You see what I'm saying? Also, doing actions in the world takes time. You know what actually is a great example of a modern AI system that did recursive self-improvement? You see it every day while you are going around camping. Waymo. When Waymo technology started, 2004 is when Sebastian Thrun essentially won the DARPA, desert challenge. 2006, it was urban challenge. By that time itself, we have established that this can be done. If you, for example, have a full map of it. When did Waymo start taking actual people like you to various places? If you have been around in the valley for a long enough time, you remember that for a long time in the middle, Waymo would have actually a human in front of the steering wheel still while it is going around the places. What were they doing? They were collecting experience. And they had the human in the loop so that if it does anything stupid, they can somehow try to stop it so that they won't get killed. Of course, if the human gets killed, that's kind of a bad thing because, in fact, you do know that Uber did kill somebody right across from, Mid Avenue, right? Do you guys remember this? The only one of the well-known, actual FSD killing a pedestrian was like in Italy. We are the crossroads of, full self-driving. Right. Our governor said, yeah, sure, go ahead and come and try it out. We have people here. Whereas California did, yes? No, this one was, they were trying FSD, and I think there was a human there, but the human basically did, react in time, essentially. Okay, that's a whole entire issue, by the way, about if you have human in the loop, the question of when to get the human to attention becomes a very interesting challenge. We are not programmed to say, ignore me until I say, pay attention, and then you must come to attention in 3 milliseconds. That's not how humans work. That's actually what happened to that poor Tesla driver who was playing stuff on his iPad, like about 5-7 years back in Florida, and then Tesla basically couldn't tell the difference between the white clouds and the white truck. So he thought it was like a truck-shaped cloud, and so it just went through it. Very, very close to it, some leader kicked in and said, hey, you may want to get up, and then that guy was said, and then out. So this issue of how to bring full automation with humans in the loop is an entirely different issue. In fact, that's where we will talk about this whole human AI interaction. It's a very interesting question. It's easier to just say, take it all over versus, and it's also easier to say, take it all over and just tell me when you need help, but you tell me with enough, with enough time for me to react. If you just say, I'll just tell you 3 milliseconds before I need the help, that I need the help right now. And if you don't give it to me, we both die. I mean, cars don't die, people die. AI systems don't die, people die. And that's a whole entire issue. So that's what happened to the Uber FSD. But coming back to Waymo, Waymo does recursive self-improvement. It's not using LLMs, not as much anyway, thank goodness. But it's doing self-improvement because it's actually making its own experience. There are two ways how people would have, two ways in which you may not learn enough about the world just from other people's experience. One is they didn't bother telling you that they had this experience. They may have thought it's too trivial a thing to tell you. What is obvious to humans is not obvious to machines. The other is they never actually, they never actually encountered that. And so that's a novel scenario. Much of what happens in the case of Waymo really is how there are just so many novel situations and you just need to know what to do. And people don't tell you beforehand. There are no simple rules. In fact, I remember Sebastian Thrun giving a talk once, like 5, 7 years back in PDDL, where he says, you will catch all these things. Like one of the things that happened when they were training the FSD with the human in the loop is so the thing was going on the road, and there's suddenly a bunch of people on ping pong sticks went through the road like, what the heck are you supposed to do? Which part of your driving license manual tells you what to do when random people go on ping pong sticks across the road? You still need to deal with it. You don't get to say, I never heard about this stuff. I'm going to just hit them gently and see what happens. Which you can apparently do in Minneapolis, but in the rest of the world, right? So my point being that, recursive self-improvement takes time. It's very costly. If you are getting the signal from the real world. If you want to speed it up, you have to depend on simulators or models. Or the LLM itself saying, I think you're right. That last part is the dumbest thing. Because if LLM actually can tell whether something is right or wrong, how come it can't actually generate? It's not obvious at all that verification is easier for LLMs than generation. Even though combinatorially, verification is easier than generation computation. That you guys realize that, right? But it doesn't matter that's not necessarily the case for the LLMs. Okay. So recursive self-improvement actually works only if you wind up doing the costly experiments in the real world. And if you do it, that's fine. You can improve. There were several questions. Question here?
I think I read the article talking about the full self. I think the human in the loop wasn't really in the loop because they were watching the movie or something.
Yeah, but what I'm saying is, why is that wrong? Honestly, this other guy was. My point is, it eventually doesn't make sense to. I understand what you're saying, but what about the poor Florida guy? He just didn't come back to senses in 3 milliseconds, right? And how about this other guy who also had the same situation in Silicon Valley, who was actually a computer guy. He was like software engineer or something, and who just basically went and hit the media and that. The question of how quickly can you come to full attention is very, very clear. Do you understand what I'm saying? And in general, again, changing tracks a bit, no. In terms of human AI interaction, have you heard of Clippy?
Yeah.
Do people think of Clippy? Why are you laughing when I said Clippy? Clippy was trying to be helpful, but it was annoying as heck. Right? So the interesting question about helping people is there are two extremes. One is you constantly tell me, say, oh, you're about to type the next letter. Can I explain to you which letter might it be or something? Versus basically wait until 3 milliseconds before you're about to die and say, maybe you should be careful. She might be dying in the next few minutes. Do you understand what I'm saying? This whole human-computer interaction is an entirely interesting area where you need to have realistic assumptions about how humans wield their attention. Yes, attention is all you need, but attention is what actually is very hard for you. Okay. So anyway, so that recursive self-improvement is basically connected to actually doing it from. This is hard because this basically, if you're doing work in the world, you can actually die. So it's easier to learn it from other people's experience. Ours, in some cases, people will actually provide you the model or the simulator. If they provide you the model or the simulator, that means they have decided this is the word. So there is no infinite fractal corner cases. The big problem in real world is there's just too many corner cases. And getting all of them right is going to be quite fast. Okay, yes, there was some other question. Yes.
About those 3 frameworks, for instance, if you have a block world puzzle case with some initial parameters, are you saying all 3 of those frameworks can produce like the optimal solution? Like
all I'm saying is here what you are developing, the thing, this block is what your algorithm is. Okay, here you have to develop your algorithm such that it can take any domain specification and do the right thing. Here you only have to do it for one domain because this is, let's say, since it's not taking the domain, that means it's assuming a specific domain. Let's say blocks world. So it will only do well in the blocks world and nothing else. Here, it's not even just the blocks world, it's assuming blocks world, right? And it's also assuming that your goal will always be to put every block on top of each other such that there's a huge big stack. And it just needs to know what the current state is.
So it's a trade-off, like that's the most computationally expensive.
Oh, that's, I think, this is, actually, computational expensiveness is different from the generality of the algorithm. We will basically see one of the things that we're seeing in terms of planning is you can have a blocks world domain model or a domain model for like logistics, domain model for some other domain. And we don't talk about progression for blocks world, progression for some other world. We just talk about progression given actions in this domain model, in this particular definition. Okay, so the point is, it's actually easier, cheaper to write domain specific anything, harder to write domain independent anything. Okay, and if in fact the particular domain is very important, why bother about you caring whether it will work for something else, some other domains or not? So one of the advantages of this is if you start here, and if it turns out that one particular domain of all the domains is most important, you can compile the domain into this algorithm, you will get this. And if you are here and you decide that a particular goal is what everybody seems to care in this domain, all other goals don't matter, and I compile that goal information in, then I'll get this. So I'm compiling, I'm specializing the more general algorithm towards more special. Okay. Any other questions? Yes.
So you talked about the, these digital world models. I know there's been some development in using physics in it as well, but what if the world model isn't an accurate, depiction of the real world, and you train your, some models in this one? Is it, at the end of the day, a good prior for like self-recursive kind of models, which can take that information to something to start with and then try to learn?
But again, the question is, it doesn't matter where you start from. The question is whether you are actually getting additional information by working in the real world, or are you using the same model? Do you understand what I'm saying? If you use the same model, then why are you expecting miracles? And if you're asking yourself, am I right? Right? Why are you expecting miracles? So there are some cases in the case of humans where you can carelessly write a wrong solution and look at it carefully and correct it. And similarly, computationally verification tends to be cheaper most of the time. It can't be worse than generation. But that doesn't necessarily hold for the way LLMs work. Okay. Any other questions? Yeah.
So you said that experience, but how do we know that how much experience is actually needed for that use case to work?
You don't. You have to ask yourself when you read people's papers. It's all about, making sure that train data and test data are the same, so that you can write your paper or you can say that it's working well. Okay, but if you're talking about actually, putting it in the real world, where things are not in your control, then it is possible that in lab on the benchmark it's doing extremely well, right? And there's this whole entire thing about what? Benchmarking. Everybody does benchmarks, right? Because that's how you are taking specific LLM models to be good or bad, etc. But just because you have the highest values on benchmarks doesn't necessarily mean that you have the best way of generalizing if the benchmarks are changed, which is what would happen here. My point is, these are the big problems. There's no pat answers. Like we can, for example, cleanly solve everything if you restrict it to like a certain class of planning problems, like classical planning, where you essentially have the domain models, and you can clearly talk about how these things are working. Now, if you then hear somebody that LLMs are planning, then you have to ask yourself, if the planning is a good planning, then maybe you should be able to do these kinds of planning because it's after all the simplest ways. If they can't, then you ask yourself, why are people thinking that they're able? And the same issue about generalization. If you trained it on certain data. With the case of LLMs, the problem is there's a pre-training, which is essentially the entire world is, they trained on the entire world, essentially, the entire world of retail world, basically. Right? And so nobody really knows what's all in the training data. And then the people do fine-tuning, which is because this is the problem I want to use. I'll get a whole bunch of extra pieces of examples for this particular problem class and fine-tune. And that's where your kind of question comes. Am I done or not? Well, it depends on whether you can change. In fact, I mentioned lost data concatenation last time, right? Which is like the dumbest problem. It's not even a planning problem. You can actually improve lost data concatenation for up to, let's say, 10 words by just giving some examples. But then it'll fail at 15 or 25 or 39, etc. At least the standard LLMs do. And the question would be, why would you want an algorithm where essentially this kind of failure to, in this case, it's a length generalization, right? That's the fancy name for why it is failing. It is failing to generalize the length. Okay, one of the things that this class gets you is a skeptical attitude towards looking at the claims. That's it, to some extent. Okay, so one of the issues would be, I remember early on once I read a paper about how like simple chain of thought or something can significantly improve planning performance for LLMs and plot support. And they basically said, there is a thing that they showed saying stat size 1, 2, 3, etc. to maybe 100, and then the accuracy. Okay, I was pretty impressed. Wow, that seems like good. But then, one of the biggest problems in current AI is the paper is 12 pages long, appendix is 12,000 pages long, and nobody reads the appendix. I mean, if they actually willfully cheat, God knows what's going to happen. Hopefully, they will just get thrown out of science. But many a time, people will just actually put it in Alpha Centauri, which is like 1100 page of the appendix. And so I basically went and looked at what are the block square problems that they're looking at. They're going from 100 blocks problem, 200 blocks problem. But they defined the n block stack as if you already have 1 to n minus 1 in the correct order, you put the nth block on. You just define it. This is exactly what they did. I tweeted this at one point. This is like already 3 years back. The problem is they didn't know any better. They just thought I need some x-axis which increases in value. Okay, right. And it's not changing the complexity of the problem one bit. It's exactly the same damn problem. Okay, so you should be careful about, because in fact, as the size of the stack increases, the combinatorics increase, and it should become a bigger and bigger search space. So the fact that LLMs are doing well would be surprising, would be impressive, but that's not what they were showing at all. Okay. Anyway, so that's that, and then there are types of computational models also depend on certain kinds of problem classes. Like motion planning in robotics is a particular subclass of planning problems which have certain types of domain models, and you can just spend your lifetime in motion planning itself. Okay, you can have task planning, which is a lot more like the general planning that I'm talking about, but it's not like doing this well gives you enough insights on the other one. In fact, motion planning algorithms typically tend to be somewhat different than the task planning algorithms. We will tend to spend more time with the task planning algorithm, which is actually a reasonable thing because most of the quote-unquote agentic systems do task planning. Okay. One other thing that I want to distinguish between is planning versus scheduling. Okay. So the difference basically is planning is finding a course of action to do. And scheduling is assigning resources to the actions that already have been decided. And in normal terminology, people call both of them planning. But really, from a computational sense, planning, classical planning corresponds to A star search. Classical scheduling corresponds to constraint satisfaction problems, CSP. How many of you have done it over here? So CSP is essentially a much simpler kind of a search problem compared to A star search. Do you see what I'm saying? So in fact, CSP problems, scheduling problems are only NP hard. If you think about computational complexity, for general scheduling problems. General planning problems, even in the classical planning of the kind of deterministic planning, can be piece-space complete. What does piece-space complete mean? What it means is it's not in the class NP. It's not in the class NP because the class NP is defined as if I give you the solution, you can check whether it's correct or wrong in polynomial. In which case, if you have a non-deterministic Turing machine that guesses all solutions in parallel, and then there is a verifier sitting under each of the branches checking, yes, you're right, or no, you're wrong, etc. So at least one of them says yes, then you're done. Right? And that verification step, if it is in polynomial time, the overall thing will be polynomial. But it's called non-deterministic Turing machine because that's actually, it's a theoretical abstraction because you can't generate in exponential number of guesses and then just check in parallel all of them at the same time. You see what I'm saying? But still, it gives you a good way of understanding where the complexity lies. Normal planning is not even NP hard. It is worse. It's not even class NP. What that means is if I give you the solution, it may still take you exponential time to check that it is a solution. And again, to understand this, you have to understand that complexity is about worst case instances. Not all plans are like this. If there exists one bad habit, remember that's the idea, right? If I give you like a bag of problems, that problem class is a bag of problems. If there's one bad habit that takes exponential time, you'll say this bag is exponential time, right? A problem class is a bug. Okay. The problem basically with domain independent planning is you can change the domains. One of the problems that you can write for in PDDL, the same thing that you use for Locksword, is Tower of Hanoi.
Yeah.
Towers of Hanoi have a mind-numbingly dumb problem, but its length of the solution is exponential in the size of the input. Which is actually why it's called Tower of Hanoi or Tower of Brahma. You all heard the story. There are these older monks who are going around in Kashi or in Vietnam, depending on which version you believe. Actually, I'll send you a picture of Tower of Hanoi that I took in Hanoi itself. Because I went to Vietnam last time when I was taking this class. The stuff that I do to actually show real examples in the class. So, but that turns out that basically the idea is if you put 64, I'm not even explaining to you what Tower of Hanoi is. If you're a computer science person, you don't know what Tower of Hanoi is. You have to do it yourself and then pick up right away. So if you put 64 tiles, 64 disks, and there's a middle disk, and you need to get them all onto the other one, is the correct one, right? It turns out that the size of the solution is 2 power 64. So 64, the n disks, the size of the solution will be 2 power n. Because of that, the solution length itself is exponential in the size of the input. Because of that, there is one bad apple in these domains. That will make it piece-space. Do you understand what I'm saying? It sort of tells you what the computational hardness is. And one of the other things is one of the other things, right? Where is this? Okay, this one. I want to show you this. So it turns out that scheduling and planning are actually in some sort of a spectrum. So in general, the typical thing about planning is To solve something, you put an action that gives that. But then that action requires preconditions. Then you put some of the actions to support those preconditions. They need preconditions. Then you put some of the actions to support those preconditions. And this is how you just cascadingly put more and more actions into the plan. This is how planning goes. Scheduling is, I've already decided that I have to go to this place, this place, this place. I need to know which car will take me from this place to this place, which driver would be driving which car, etc. That's resource assignment. And there is a spectrum in between, depend on which kind of goes from scheduling towards that. And if you see, especially in the case of LLM planning literature, they don't even know the difference. So for example, there is a Google folks basically made this thing called natural plan benchmark for LLMs. First of all, you wonder what is natural, what makes it natural? Is it because Google made it? More or less that's the thing. Basically, they said it's natural planning because planning specification is written in natural language, which is like a dumb way of describing. I'm hoping that they're not Google ways. But more importantly, all their problems are things like trip planning, meeting scheduling. They're all scheduling. You see what I'm saying? I'm not saying that scheduling is easier than planning for LLMs. It turns out that actually computational complexity has no connections to how LLMs solve problems. We'll keep saying this multiple times during the semester. But you should at least know what problem we're trying to solve. So natural plan is actually a scheduling problem. Whereas Block's world is actually a planning problem because there is cascading choice. Okay. Yeah, so then I told you about how the environment types make things harder. I already mentioned this. I also talked about the distinction between planning, generally scheduling, and then reinforcement learning, essentially. These are like densely written slides that I used in an ICML tutorial, and I went through them in like 5 minutes. But you're getting the entire class of this. But basically, you only expect, if you already know it, you can do it in 5 minutes. Otherwise, you just hear me. That's about it. Okay. So anyway, so this is planning the scheduling, and the reinforcement learning is essentially you're learning the model too on the way. Okay. And we talked about algorithmicity, robustness, quality, optimality, and here's a slide for that. A densely written slide again that I used in the ICML tutorial. But you can look it up more carefully. But that's basically what. Again, one of the other things that I have to explain to this. I mean, I know that many of you like the word ergodicity, especially because I said that's a good jargon word to remember. So you wrote that as the today I learned thing. I was also teaching about ergodicity to the New York Times reporter. So not in fact, the word ergodicity shows up in New York Times day after, next week, you know who to blame. Okay. Because once again, if you're doing recursive self-improvement in a world that is not ergodic, you die. Right? And that's going to be an issue and you have to deal with. And agentic systems have to be carefully stabilizing themselves so that they only look at the words where they can't get into trouble. Okay. And then we talked about world models, verifiers, and simulators. Again, one more slide. So really, these last 3 slides were the last 2 classes. But you can decide if you understood this already, then you probably wasted a whole entire 1.5 classes. If not, then I basically dragged you through pieces of try to hopefully give you some intuition. Okay. That's where we're going to go. The next that we're going to discuss is this whole operator planning stuff, which you read about. And this is where, in essence, we are looking at this part, where you get to write, you need to write the domain model, and you need to write the initial state and the goal state. The simplest idea you might think is, why can't you write it in English or some language? Well, one of the things you will see is originally, most of the AI systems developed with some specific formal languages. And one of the advantages is LLMs is you can actually specify things in English and they might still do something. So one interesting thing, even before I go forward, is you guys all read what PDDL looks like, right? And I guess you instinctively hated it because it has parentheses. right? I mean, people hate Lisp. I don't understand why. I love Lisp. I feel that the world has gone down ever since Lisp started being used. But people don't like parentheses. They feel as if they have to count. The whole point of computer science is you don't have to count the parentheses. Computer counts it. But anyway, so you may not have liked the way the PDDL looks. Okay, so one thing you can do, which people have written tons and tons of papers, and they continue to write these papers, is take the block sort problem in English. Ask an LLM to convert it into PDL. And then ask it to go to Rao's class, which will tell you how to go from PDL to plan. I'm not kidding. This is basically a very bad way to use LLMs, I would say, because why spend so much money and effort to train LLMs if all they're doing is just convert it from English to PDL? On the other hand, it's just available, so why not do it? LLMs in general are amazingly good at format conversion. Right? So that is one thing you can do. So if you're thinking, as of now, why is he now making us think in terms of PDL? Don't worry about that, because you could have written in English and you could have trained, fine-tuned a model with this is the English, this is the PDL, this is the English, this is the PDL. You start making new English in new PDL. There will be some errors. Nothing is ever correct in LLMs. Right? Not guaranteed correct. So then you can look at it and say, oh yeah, there is extra something missing or something, and you put it in, and then you can leave it. But my argument is that, so if you do that, then at least the English part, English versus PDL part is dealt with. If you just hate the part about PDL. One of the other things that is actually a lot more interesting is to see if in fact LLMs can be made to do planning itself, which is what we'll also do on the panel. But you can see what I'm doing, right? How many of you seen Memento? The movie? Yeah, what else is there? so for those of you, you should see it actually. Memento is just an amazing movie. So for those of you from India, see Ghazni, which is a cheap knockoff of Memento. Actually, I saw some new movie recently, which was Tenet is crazy. This is other movie that was like I was going around saying Memento plus plus. I'll tell you after I'll tell you after the break. But Memento is a great movie. But it turns out that, I should tell you or not, but in the interesting way of understanding Memento, and for those of you who haven't seen the movie yet, close your ears a bit, is there are like two strands and they both meet in the middle in a weird way. So there are two reverse strands and they both meet in the middle. Okay. And to some extent, this course is sort of like that. There is how to generate plans from classical techniques, and there is how to get LLMs to do planning. And I'm sort of, rather than complete one and start the other, I'm sort of doing it in a weird interleaved fashion. I have told you my version of what LLMs do. I'm assuming you know something. So that's why this is the reverse part. Eventually, at some point, I'll say my version of LLMs is that they're N-gram models, and then I'll be done with that. But that's the introduction for LLMs, but I'm already talking about how to use them for that. Okay. Anyway, so operator planning, we're trying to do goal-directed behavior. Domain-independent planners, as I said, handle the input on. They just require the domain as well as the initial state as well as the goal state. And we'll be talking mostly about domain-independent planning. And the question is, what is a model for this planning systems? The simplest idea is atomic models. Okay, in general AI, to understand any problem, you start from what's called atomic models, then you go to state space models, then you go to relational models. That's one way of thinking about how to model the world in more and more compact fashion. Okay, this would make sense to people who did intro to AI. Okay, so an atomic model essentially just says there are states and the actions make you transition from state to state. And each action is defined in terms of this transition matrix. So, in particular, to go to the atomic state, essentially, so a transition system is essentially an S and A. S is a set of states, A is a set of actions, and the action is defined as a matrix. Right? So, this particular action, it turns out if you do it in A, it takes you to B. If you do it in B, it takes you to F. If you do it in F, it takes you to E. If you do it in E, it takes you to B. If you do it in C, it stays in C. If you do it in D, it takes you to C. This is my action. This is one action, A1. And not even action. In fact, since we are talking about states as A, B, C, D, etc., think of this action as action 1, right? This action can be written in the first principles way, this way. So here are the states, A, B, C, D, E, F, A, B, C, D, E, F. And so if you do it in A, then you go to B. So you put 1 into B. Right? And if you do it in B, you go to F. So you put 1 in F. If you do it in F, you go to E. You see what I'm saying? Right? And in this particular case, it's a total function. That means the action is defined for every state. That action's effect is defined for every state, including this particular state C, for which when you did it, it actually stays in C. I would say this is a deterministic action. Do you guys get this? If this were to be a stochastic action, what would change?
Action would be
Yeah, what?
Per row, the sum would be 1, but each individual value will be some fraction between 0 and 1.
Exactly. Do you guys get this? So if in fact, it turns out that if I were to do the action in A, right, I would actually, let's say, I really want to say that when I do this action in A, it will go to B with 0.7 probability, C with 0.3 probability, and remain in, 0.2 probability, and remain in A with 0.1 probability. Let's say. So then the row for A would essentially have 0.1 here, and 0.7 here, and 0.2 here. You guys get this? That's it. That's the stochastic versus deterministic actions. That's a transition model. Not surprising at all. Now, if one of the issues is that plan is if I'm in a particular state A, so planning in this way is essentially graph traversal. But essentially, the normal graph traversal says if there's an edge, then you can go. Right? Here, the edges are determined by the actions. Did you understand what I just said? So if there is an action A which corresponds to these edges, there may be an action 1, this corresponds to these edges. There may be action 2 that corresponds to different edges. And what you're trying to do is decide which action to do after which action to do after which action. You see what I'm saying? So given this matrix representation, suppose if I say my plan is action 1, action 1, action 1. And I am in state A. Then what happens? So I'm in state A, action 1 takes me to B. Then one more action 1 takes me to F. One more action 1 takes me to E. That's a plan. So if you just wanted to go from A to E, the action 1, action 1, action 1 is a 3-action plan to go from A to E. You get this? Okay. So one of the interesting things is you can actually do planning as just matrix multiplication. Right? You take all the actions. So if you say there is a plan for, your plan is action 1, action 2, action 3, action 4, then you just take the matrix for A1 multiplied by the matrix with A2, multiply the action with A3, multiply the action with A3, A4, you get a new matrix. That new matrix tells you the new adjacency. So it's essentially the transitive closure. What we do is transitive closure with the actions. Do you see what I'm saying? So if you wanted to see whether A, I'll get there. If you wanted to see if A can ever reach D after these many things, after let's say action 1, action 2, action 3, then you look at the final matrix, action 1, action 2, action 3 matrix, and see if in the A row there is a 1 at D. If there's no 1 at D, that means you can't reach. Yes.
Where is the second matrix coming from?
That is a different matrix, basically. That's what I'm saying. So each action corresponds to a matrix. Okay, so in this particular case, I'm actually using the same matrix. No, actually, no, I'm using a different matrix. So there are two different actions. Each action corresponds to an adjacency matrix. So each action corresponds to a matrix like this. And if you have two actions, then you have two matrices.
And so what's the product of the, or like the multiplication of the two matrices?
It is basically telling you after, if you just, what is this single matrix telling you? If you are in A, you could reach B after this action. If you are in B, you could reach F after this action. If you do action 1 times action 1, which is a plan 2, then that matrix will tell you if you are in A, where would you be after the two actions are.
Oh,
It's you guys realize this. I just put it in the matrix format. Okay. One of the funnier things is these are basically, atomic representations. And the problem with the atomic representations is that they're as big as the state space. It's kind of nice to see it this way. But if your state space is, let's say, million states, you're talking about million by million matrices. Right? And you might say, that's one thing modern AI is good for, multiplying huge big matrices, because we spent entire computational infrastructure to do multiplication of big matrices possible. Right? That's one thing we can do, honestly. But the real question is, think of a world. So the one of the issues is, in the worst case, an action can, in essence, take you from any state to any state. Any arbitrary state to any arbitrary state. Different actions will take you from arbitrary states to other arbitrary states. If you really have to live in a world where actions are that powerful, we probably won't be here talking about that. We would basically have died. The evolution would have killed our entire place. The reason we can actually live to some extent is, okay, first of all, let me complete this, I'll get to that. So deterministic planning and atomic transition is just pathfinding in graphs. And then you can just basically do any graph search algorithm with respect to this. Okay. And I'll get to MDPs later, but to some extent, the only thing that's different about MDPs is they'll also allow stochastic actions. That's kind of important. And then I told you how to deal with that. Transition models in MDPs will correspond to not zeros and ones, but basically numbers between 0 and 1 that add up to 1 per row, as the gentleman said. Okay. Now, this is what I want you to understand before we take a break, and we'll come back to PDDL now. Okay. What I want to say is transition systems are a great conceptual tool to understand the differences between the various planning problems. Because that underlying it all, whether you do planning this way or this way or this way, you can always talk about the first principles, what's going. They might be using different formal languages, they might be using different representations, but in the end, underneath it all, it's the same. You guys know this? Limit h tends to 0 as x plus h minus fx by h. What the heck is that?
differentiation.
Yeah, these guys are undergrads. Grad students would already should that. Right? This is basically first principles definition of gradient. First principles definition of differential. How often do you actually do it that way? Suppose if I say what is the different derivative of sin x, you're supposed to say derivation of sin x. Oh, let me just start doing this. Sin x plus h minus sin x by h, limit h tends to 0, and you start doing this. And if I say what is the derivative for sin square x, you do it for sin square x. If I do tan cube x, sin square x, you do it for that, and the exam is over, right? Because you haven't yet computed the limit. Nobody does it this way. This is important because it's the first principles approach, but we generate a huge number of shortcuts. That will make it actually doable to get to the chain rules and all sorts of things, the multiplication rule, and also some of the remembered derivatives, classical derivatives, e power x is e power x, sin x is cos, all that stuff, you kind of know that. Right? So, to some extent, this will always work. But nobody does this most of the time. Think of atomic transition systems that way. If in doubt, you can always try to understand what a system is doing at the atomic level. But it's going to be very inefficient. In particular, it's going to be extremely highly non-compact. If you have a world with million states, each action will be of the same size, million by million matrix. Do you understand what I'm saying? What you want is a compact representation for the actions. How will you get the compact representation? It turns out that if you can hold, let's say, that the world is made up of state variables. World is made up of state variables. You can hope that the world is made up of state variables. And for now, machine learning people, features. And that makes you feel much better. Okay, state variables are Boolean features. If you can define the states in terms of features in the state, and if it's a complete description, that means if you give the feature description of the state, then you are completely described the state. And if there are n features, and if there are n Boolean features, then how many states are possible? 2 power n. In general, I say that in computer science, if somebody says, what is the answer? You can always say 2 power n and you'll be right most of it. Right. Right. So if there are n state variables, then there are 2 power n states, right? Because you need a state is defined as a valuation for each of the Boolean fluids. So the first fluid can be true or false, 2 possibilities. Second fluid can be true or false, 2 times 2. Third fluid can be true or false, 2 times 2 times 2. Nth fluid can be true or false, so 2 times 2 times 2, n times 2 power n. You see what I'm saying? So then if you speak of the states in this way, if it is actually possible, remember that this will always be, I mean, the transition model representation will always be possible, but this fluid model, feature model representation possible sometimes, not possible sometimes. Just as fx plus h minus fx by h will always work. But every once in a while, you will have crazy derivatives for which you don't have closed form solution in derivatives. Right? Why? Because you can't do it in the usual chain rule, etc., where you just have to write it. Either you have to make up a new name for the function, right? You guys know there are derivatives. So it's even more so for anti-derivatives, the integrals, but certainly true for derivatives too. There's lots of functions for which there's no closed form derivatives. But that doesn't mean that they can't be derived, that they can't be differentiated. It's just that you can't write it in the language you have. You understand the distinction? Whenever you take a representation language, it also kind of reduces, it limits your expressiveness. You see what I'm saying? Which is basically what they say that, Eskimos have 32 words for types of snow. And they have probably no word for heat. Phoenicians have 32 words for types of heat, and they have no words for Phoenix people, not Phoenicians. Okay? They have no words for, probably snow, because they never see it. You see what I'm saying? So what you can express depends on the language that you are using to some extent. Okay. So in the case of transition matrices, basically, if you have this sort of, first of all, if you can say that there's a compact number of features, let's say n features, that can be used to represent your state space, that's an exponential reduction. Right? Instead of 2 power n states, you now only have n state variables. So instead of million by million matrices, now you are thinking in terms of log of million is the number of variables. And then the actions will be defined in terms of how they change the state variable values. Do you understand what I'm saying? So they doctor the state. You have a state which has all the state variable values. when you do an action, it basically changes the values of some other variable. That's exactly what you saw in the PDL. We'll come back and see it again if you don't remember. But that's exactly what happens when you say stack xy. Stack xy will make sure stack AB, if you do it in a state, if you do a stack AB, then it will make sure that the value of on AB will be true after this action. You see what I'm saying? So I'm constructing the state, doctoring the state. If you do this, then you have transition models, what are called the factored transition models, or compact transition models. Do you see what I'm saying? So the size of the explicit graph corresponding to the transition system is too large. Oftentimes, the remedy is to provide compact representations for transition systems. Start by explaining the structure of the states. If the states are specified in terms of state variables, that would help. Then represent the actions not as instance matrices, but rather functions specified directly in terms of the state variables. What do they do to each other state? The next thing is, this doesn't necessarily mean that the actions will be compact. You can have an action that is highly conditional, and it will say that under such and such cases, I will make this variable have this value. And in a slightly different cases, I'll make the variable have a different value. So you need to then make another assumption that most reasonable worlds will have the property that actions only change a few of the state variables values, and in a few different ways. In which case, then you get to write it as a nice Scripps action or the PDL action saying, this variable becomes true, this variable becomes false. You understand what I'm saying? In doing so, whatever can be done by Scripps can be made sense of in the transition models, but not vice versa. There can be things that you can do in transition models that may not necessarily be expressible in Scripps. The same way with fx plus h. Whatever that you can do using multiplication rule for the differentiation can be made sense of using fx plus h minus fx by h, but not vice versa. There are things that you can do in the first principles that cannot actually have simple closed form. So basically, when you get to strips, which is this, and I'll stop right here. We'll come back in a minute, but take any strips world where essentially they talk about state variables, that are the features of the variable state. And then the actions which are talked of in terms of how are the features going to change when you do that action. And if the action tells and then there's an assumption called Scripps assumption, which says if the action essentially what Scripps assumption is that it says every action must specifically state its effect on every one of the state's units. If you say so, then you can use closed world assumption. That means if I tell you that I'm going to tell you all the variables I'm going to touch, and I say these are the only variables I touch, that means the rest are not touched. So if there are 100 variables and you have an action, the first thing you do is you copy all those variables and their values into the next state. Then you just change the values of the variables that this action is actually changing. And you have a new state. That's PDDL. And psychologically, there's a good enough, there's some reason to believe that we tend to think of the actions in the world in terms of what is required to do them and what will they change. So it's actually a very reasonable way for us to think in terms of actions. And the PDL and Scripps models basically go off from there. So you're essentially generating plans in terms of these kinds of representation. So let's mull over this, come back at 3 o'clock. We will do that. Oh, I remembered the movie the thought was Memento Plus Plus. It's actually a Malayalam movie that I saw on Netflix called Pushkin the Kandam. if any of you are Malayalis, yeah, that actually is Memento plus plus. Yeah, sure. Just give me a second. Okay, okay. Okay. So, you can hear me, right? So basically, that's how we get here. So the transition model, atomic transition model is the common ground for across everything. It also works even for continuous state spaces. So basically, state, action, state is the way you think in terms of. That's why, like in general, when you see any random RL paper, for those of you read that, they are always talking in terms of SAS dash. Is a trajectory. You are in state, you are in action, you get to the state. Okay. By the way, here is an interesting question, just for the heck of it. If you have a stochastic action, and then basically you're doing the actions, A1 and then A2 and A3, would the trajectory be S followed by A followed by a set of states, and then another set of states followed by the next action by another set of states? You understand what I'm saying? So is it going to be always SA S dash format, or is it going to be more like SA set of actions, S1 SK? Because stochastic actions are supposed to take you to the set of states. Which one? What? Which one? The set of states. Okay. How many people think that if you do stochastic actions and you actually do the stochastic actions in the world, then the stuff that you see in the beginning is the state, and after they do an action, you get a superposition of states, and after that, you get a superposition of states.
If I have already taken the action, doesn't that make it deterministic? Yes.
I don't know. I mean, apparently there are people who toss coins and then they just stay in the world with like a what is that? The Schrodinger cat, like it's both heads and tails, and now I toss once more, it's heads and tails, heads and tails, heads and tails. You know what I'm talking about, which is if you are looking at the state action sequence, if you are an agent and you have stochastic actions and you're doing them one after other, you still see state, action, state, action, state, action. before you do this action, you don't know which state you will be. After you do it, you will be in one state, not a superposition of states. Do you understand what I'm saying? I mean, if you are worried about that, think about, suppose I'm about to do the action of tossing a coin. Okay, what do you think will happen? May it come tails, it may come heads. But I actually did it. Will it come both heads and tails? No, it will only come one thing. The nature resolves the uncertainty. Do you understand this? Okay, so SAF dash is always the sequence of state actions, state transitions that you will find if an agent is doing something in the world. One of the fun parts about that is that if you see somebody doing any behavior and you're trying to learn from them, then at best all you can do, I'm going to take these up now. Is that they always look. They always look. Please pay higher tuition, guys. They raised it by next time, remember, can you remember to get one of our classes? Anyway, so all I'm saying is whether you are in a whether you are in a stochastic action, stochastic world, or a deterministic world, when you do actions, you see behaviors that look like that. The only way you would figure out that you are in a stochastic world is, let's say, sometime later, you did S and A, it went to S triple dash. Then you know that the same action from the same state is leading to a different state. So it must be stochastic. Do you guys understand what I'm saying? So this is actually what happens in reinforcement learning, right? Basically, to compute the transition model, what you do is you take these kinds of behaviors and count the number of times A1 has been done in S and see which fraction of them went to S dash, which fraction of them went to S double dash, which fraction of them went to S triple dash. That will be an empirical estimate of the stochasticity of the action. You see what I'm saying? Okay, so since I said this, when will you actually get into a situation where, at least from you, the agent's perspective, this is, by the way, the reason why it's called fully observable. So MDPs, again, I'm assuming, how many of you have heard of MDPs? Okay. MDPs are fully observable. The classical formulation of MDPs are for fully observable. They allow stochastic actions, but after the action is taken, you know which state you are in. You see what I'm saying? Okay. That's basically, and so that from that perspective, let's say deterministic planning or stochastic planning, behaviors look like this. So when will you actually, from the agent's point of view, when will it happen that you start from S and goes to from A, and it has A1, and then you go to a set. Even from the agent's perspective, it should be the case that it can't actually tell which state it is in. Even after the action is done, it can't actually tell which state it is in. Have you seen a problem in this class that is like that? You guys wrote that as one of the today I learned. Bomb in the toilet bomb. after you basically, after you flush the package, did you know whether there was a bomb? And you flush the package and there was not a bomb and you flush the package. Did you know that? No. You only know that you're safe. You still don't know whether the damn package had a bomb or not. That's what partial observability does. You understand what I'm saying? Full observability means you're always going from state to state action state, whether the actions are stochastic or deterministic. Full observability means the behavior is always state, action, state. People should be writing this kind of stuff because I can ask you, you should know this area. Okay. But if it is partially observable, then you can go from single state to a set of states. And of course, a set of states to another set of states, even at the behavior level. Okay. You need a name. You need a name for the set of states. You have a name for, so you have name for states and then cap states, right? So if you want to have a set of states, what should we have it as a name? Belief state. It's called a belief state. The agent believes that it's in one of these states. Okay, so a set of states is a belief state. Okay, now let's do this following fun part. If you have n state variables, then there are 2 power n states. How many belief states? How many belief states are there? Yes. When in doubt, just keep using it. So it's 2 power n. Right? Because the number of subsets of a set of size n is 2 power n, right? If there are n elements in a set, the number of subsets you can make of that set would be 2 power n, right? Because each in the subset that you're constructing, you can put an element in or not in. You put it in, it's one possibility. Not put it in, it's another possibility. So for each element, there is 2 possibilities. And so 2 times 2 times 2, 2 power n. But this n is actually states, which in itself is 2 power n. Actually, so what we are saying is 2 power s, where s is the number of states, which is 2 power n. So it's 2 power n. So the number of belief states is 2 power n. Now, imagine that what's the point in when I say a belief state is S1, etc., S15, I'm not telling you anything about which is more probable, which is less probable. Right? They're all non-deterministic. One of them will have. But if you happen to know the probabilities, that's more knowledge, right? Yeah. It's more knowledge. Right? If you happen to know the probabilities, then you can essentially have S1 to S15, where each of them is 1/15 probability. 1/15 probability. That's one possibility. Right? Another belief state, which is distinct, is S1 to S15, and it's 0, 0, 0, and then half. S14 and 15 are half possibility, and all others are 0. You see what I just did? How many stochastic belief states are there? You just so how many stochastic belief states are there? So all I need is just find a number of real numbers that are between 0 and 1, and they add up to 1. How many possible ways can you get n real numbers that are between 0 and 1 that add up to 1? What?
Is that infinite?
What do you mean, is that infinite? You are the grad student, you tell me. Anybody can do infinite minus 5 or something for him, so that we get less than infinite. Do you guys see what happened? The number of probable, when I did this, it is a distribution over states. the number of distributions over 15 states is infinite. Weird thing. If you have probability, you have more knowledge. Compared to non-deterministic, where one of these things happen, I don't know which one happens more likely than other one. Your life was easier in some sense because there are only 2 power 2 power n beliefs. If you know the probabilities, then it is actually infinity. Knowledge is bad. I told you this before too, right? Essentially, sometimes life is easier if you don't have eyes and ears. And it's also easier if you don't have probabilities. Because nobody expects you. The poor guy has no probabilities, so he only has 2 power n square, 2 power 2 power n square, He's ignorant. We won't admit him into grad school or anything. We must hire into grad school, but they will make money anyway. Right? Hello, excuse me. Are you in this class? Are you in this class? Are you just taking rest here? Are you in this class?
Yes.
What's your name?
Mitchell?
Michelle. Okay, send me an email. Thank you. Okay. This is what happens with me. Okay, so I will ask you if you are doing that. So what is it? So basically, number of belief states, stochastic, in the case of stochastic bandwidths, is infinite. So even for a discrete state space, the space of belief states is continuous. You understand what I just said? Imagine you have just 2 states. S1 and S2, there's only 2 states. Right? The number of subsets is 2 power 2. That's no states at all. Just S1, just S2, S1, S2. Number of stochastic belief states is any 2 numbers that are between 0 and 1 and that add up to 1. So that is X plus Y equal to 1. So this is the belief space. This is the belief space. Every point here is a belief state. If you have 3 dimensions, that means you have 3 states. It will be a plane such that X plus Y plus Z is equal to 1. So I'm very bad at drawing, but I'll try. One, and we take up axis. Is a name for these things. You know what this is called? What? No. No. They're called simplexes. This is a 3-dimensional simplex where all values are positive, all coefficients, all the dimensions are positive, and they add up to 1. This is a 2-dimensional simplex. If you have more than 3 dimensions, God help you. Because you can't try, but it still exists. It's a 10-dimensional simplex. But notice how we went from discrete states to continuous space. If you had discrete state, you were in discrete space. But then the moment you had uncertainty about, if you have observations are partially, if the world is partially observable, if your world is partially observable, then you are actually in 2 power n space, and if it's partially observable with stochastic information, that means probability information, then you are essentially in a continuous space. Okay, it's actually extremely useful to understand this because we'll come back to it much later, maybe, but maybe some of you may have heard about it. For example, that algorithms like policy gradient algorithm for reinforcement learning, essentially, basically, they have to differentiate. To differentiate, you need to go away from discrete to continuous. And so what you'll wind up doing in those cases is you will essentially take for the MDPs, this part you may not understand right now, we'll get back to it later. You will wind up having a stochastic policy. And the moment you have a stochastic policy, you can make small continuous tweaks to it. You see what I'm saying? So in general, there is this connection between stochasticity and going from discrete to continuous space. But anyway, leave that alone for now. Go back to a happy life of discrete worlds with Bloch's world, right? And then basically, yeah, all I want you to think of is these are all essentially Boolean state variables. On table A, on table B, clear B, hand empty, they're all Boolean state variables. And I basically told you what are the values of the Boolean state variables in the first state, initial state. And I'm telling you exactly what I want in the goal state. And two things are important. Even in this simple scenario of classical planning, initial state is completely specified. Actually, for it to be classical planning, initial state must be completely specified. What that normally means in general is if it is anyway completely specified, and these are Boolean state variables, then I can just go ahead and say what is true, and the rest are all false by definition. Do you understand what I'm saying? If on the other hand, I say, I'm only telling you the ones I know, then I better tell, I know this to be true, I know this to be false. Do you guys understand what I just said? Right? These are what are called closed world assumptions. Okay, so if you happen to know that everything is going to be mentioned, if you must give the initial state to be completely specified, then I might as well just say, I'll only tell you what is the positive, and then by definition, I'll tell you what is negative. And it's the same thing for the skips assumption about the actions. If I know that action is going to tell me every variable it's going to change, then I can just say, tell me only the variables that you change, the rest I assume are not changed. You see what I'm saying? Okay. So in this case, basically, what we wound up doing is like it's saying, forget about preconditions for a minute. The effects basically are saying, if I do the pickup x, then whether or not holding the variable holding x becomes true, and the variable on table x becomes false, and the variable hand empty becomes false, and the variable clear x becomes false. Again, think of this as a feature representation with 1 and 0 values. And true means value 1, and false means value 0. If you want continuous features, you can have continuous value. Multi-valued features, you can have multi-valued. But strict assumption, most of this stuff is basically for Boolean. This is what I'm saying. And the other interesting thing is about goals. Unlike the initial state, where you say everything that is true in the initial state, in the goal, you only need to say what you care about, not everything else. This is normal. Right? You want to pass this course. That's your goal. But on the day you got your grade and you passed, if you think of that state on that day where you found this, that state has infinite number of state variables, including the color of the shirt you are wearing, the length of your hair, the face, the expression on the face, how tall you are, or whether or not US exists as a country. All this stuff is state variables. All I'm saying is, I don't care the rest of the variables. you just pass. That's your goal. You understand what I'm saying? Goals are always partially specified. Because you only specify the parts that you care about. Okay? What that actually means, see, the incompleteness, the completeness assumption holds for the initial state. So when I wrote initial state like that, that means that everything else is false. When I wrote goal to be not clear B and hand empty, that means everything else can be either true or false.
No, I mean, you can end up with multiple goal states too.
Of course. That's exactly the possibility. You could fail this class while wearing a red shirt. You can fail this class while wearing a green shirt. You can fail this class with US existing. You can fail this class while not US existing. Everything is still failing. Or us, which depending on the work. This is extremely important to understand. When I say goal, there are multiple states of the world which satisfy the goal criteria. If you remember again intro to AI, A-star search has a goal test. If it comes out saying true, then it's a goal. It can say true to many, many states. I would actually argue that asking people to specify the entire goal, every possible condition, the value of every possible state variable, even these kinds of simple words, is a burden on the user. They won't care less. They just wanted these things. You should make sure that the rest takes whatever value possible. The problem basically means that a goal corresponds to a set of states. In classical planning, goal, quote unquote, goal state merely corresponds to a set of states. Set of complete states. The problem with the set of complete states is, imagine you have S1 and S2 are the only states, right? The set of complete states. So imagine what I mean is, yeah, S1, S2 are the only states. So I want to talk about sets of states. What are the sets of states if I have just S1 and S2? I can have S1 alone. I can have S2 alone. I can have S3 and S2, 3 states. But remember, the total number should be 4. What is the fourth one? No state. No state. What does that mean? Imagine my goal is on a B and not on a B. That's my goal. It's not solvable. Even though it looks like it's possible, you might say, well, this is pretty obvious. You said A and not A. How can it be possible? Well, I'll tell you something else. Imagine my goal is on a B on CB. Is it a feasible goal? No. What makes it unfeasible? There's nothing against each other, right? It is just that the domain physics is in such a way that from any legal state in the blocks world, you can never get to a legal state in the blocks world where both A and C are on top of B. Do you understand what I'm saying? Okay. Think of the following other one, which will come to haunt you later. Oh. My goals are clear B and hand empty. I only have 2 blocks in the world. A, B, and let's see what was that. Oh, wait, no, that's not the correct one. Oh, yeah, okay. Yeah, not clear B. And let's make it this way. Not clear B and holding A. Okay, and my blocked board problem is that missing. Not clear B and holding A. Actually, even more interesting, not clear B and not handled. That's my goal. There's nothing definitely obvious that these goals can be achieved. But the physics of the domain, which is a pretty transitive thing because the initial state and the actions define the kinds of reachable states. It turns out, given this initial state and the kind of actions you have, it's impossible to make B not clear. To make B not clear, you have to put A on top of B. At which point, actually, it should not be not hand empty. It should be, if you put hand clear, it's like holding it. At which point, A has to be hand. Okay. In general, let's say actually it's not completely correct. I'll show you the exact example since I'm living here. I don't want to mess it up. Shish. Come back to this. Yeah, this one. Yeah, this is my example. So here, I'm actually jumping ahead because I confused you with the bad example. I want to get the example right. Okay. Here, I want to actually start from the goal. The goal is not clear B and handle it. Right? And I want to not do progression but regression. That means I want to construct the plan with the last action first. We'll get into the actual mechanics later, but I could basically have the last action we put down A, last action we stack AB, last action we put down B. Right? Now, then if you do put down A as the last action, then, as you kind of read, and I'll again say, basically, if this is the last action, then it would basically not violate, it should not violate anything here because this is the last action. If it makes one of the goals untrue, then you're screwed because there's nothing you can do afterwards. And it should hopefully, for it to be useful, it should give something. So put down A essentially gives you hand empty. That means I need not clear B still before. And then to be able to do put down A, you need its preconditions, which is holding A. So now, instead of this being the goal state, when I say goal state, I really mean set of complete states that are consistent with this goal state. I'm now going to recursively do the same thing from here on. Right? And similarly, I could have considered stack AB. If I considered stack AB, then I would basically, if I do stack an AB, then not clear B will be true. Right? So I don't need not clear B here anymore. Stack AB will also gives me hand empty. So hand empty doesn't have to be true either. But then I would need holding A and clear B. Holding A and clear B. So the word initial state in this case, if you look at it there, so initial state, let's see. Yeah, so one is holding A and clear B, one is not clear B. Why am I blanking out here? Not clear B and holding A. One of these actually turns out to be unreachable. Which is unreachable? Yeah, so this one is unreachable. right? Starting from that initial state, you can never reach this state. Do you guys see this? It's just 2 blocks. This, it looks like a good thing. Interestingly, you can do regression from this. And you can regress all the way. One of the beauties of a state search is a dead state gives even more dead states. And you can waste your time looking at that entire space. Okay, this actually is basically to say that the fact that the goal state is incompletely specified by definition can be either a good thing because you are not wasting time trying to worry about the irrelevant details, and it could also be a bad thing. Right? Which is, for example, I will tell you, okay, you just have to do this. Among your boss, I tell you, you have to do this, and this. And it's truly doable if you don't have any other life. And you have a life, so you can't complete this class, so it's infeasible for you, but I don't care. I just gave you only reasonable goals, what it looks like a reasonable goals, but your physical constraints made sure that you can actually never reach that close. You understand what I'm saying? So actually specifying goals partially means you can actually have goal states that are unreachable. That means their actual set of legal states corresponding to this is, basically empty. Yes.
Even if the goal wasn't partially identified, it would still be impossible, right? Because there's like 5 variables. So if you did define all 5 as the goal state.
Yeah, but the interesting thing is then it becomes obvious. The interesting thing basically is this will come up again and again. We will talk about this idea called Sussman anomaly in a minute. And it turns out Sussman anomaly actually is not an anomaly if you say what happens to all the blocks. It's only an anomaly if I tell you, just the cases that I want. I want on AB and on BC. If I don't say on C table, if I just say on AB and on BC, you probably thought on AB and BC, obviously where will C BC will be on the table. Okay, but if I don't tell you on C table, then you don't have that as an explicit goal. And if you don't have it as an explicit goal, it turns out that in the case of Sussman anomaly, if you work on AB, then you try to work on BC, you would have undone the first goal. And if you work on BC, then you try to do the on AB, you would have undone the first goal again. So there's no way you can actually achieve goals one after the other without undoing the previous goal. That's why it's called Sussman anomaly. There is a Wikipedia page for Sussman anomaly. And the reason it is Sussman anomaly is because the goals are only specified in terms of on AB and on BC. The on C table is another piece of the goal that I didn't specify. Turns out the only complete state where A is on B and B is on C is also C is on table. But I'll let you figure that out. Do you understand what I'm saying? So, for example, suppose I say you should get an A in this class, and you should also be very sad at the end of the semester because you had no life. Then it's very clear what your goals are. But if I just said you have to only get an A in this class, then you will find out that by the end of the semester you did have an A, but you are also extremely sad because you had no life. I'll let you figure that out. You see what I'm saying? That's the interesting part of giving partially specified goals. You can give goals that are mutually exclusive sometimes. Anyway, so let me go back. Yeah. Yeah, so that's blocks hold, right? So then basically these are the effects on the, and the thing about preconditions is this is one place where the actors become not total functions. So to some extent, if the preconditions are not satisfied, then the action is, the outcome is not defined. You understand what I'm saying? And it's actually the way Strip's action representation is written. That means if the preconditions are not satisfied and you try to do the action, the world ends. Just ends. Like kaboom. And it turns out that that actually makes life much simpler in terms of search. Having precondition makes search easier to control. But in realistic worlds, preconditions don't actually exist. Imagine to be able to lift this, table, my precondition should be that I should have superhuman strength, a reasonable human strength, which neither of which I have. Okay, so if I not try to lift it, the world didn't end. Even though I did have the strength when I tried to lift it, the world didn't end. It remained the same as. So in fact, to do that, you have to have what are called conditional effects. Conditional effects say actions will always execute, and whether or not they have a particular effect depends on whether or not something was true before the action. Okay, so in fact, there was a conditional effect in this example. This is one-way rocket domain, not Bloxworld domain, it's one-way rocket. Okay, all that is saying is there are two packages on the Earth. There is this Apollo 13, which just basically, goes to, if you say go, it goes to moon. You are interested in getting both packages to the moon. So the actions would be put in package A into the rocket, put package B into the rocket, and then take the rocket up, the rocket takes off, and then on the moon, take the package out, package B. Okay, right? Now, it would be very easy if you want to say that the rocket won't take off unless A and B are inside. That's like saying planes should not take off unless I'm actually there, which Trump can say, but you can't say. Right? So the planes will take off. Whether or not, suppose the plane to New York and you want to go to New York, the plane will take off whether you reach the airport or not. Whether you will be in New York depends on whether you were in the plane to begin with. So you being in the New York is a conditional effect. Plane being in the New York, once it takes off, it will be in New York. I mean, there's a modeling issue. I mean, you can also start talking about asteroids hitting planes, etc. That I'm not modeling. Okay, so once plane takes off, it goes to New York. But whether you will be in New York depends on whether you are in the plane. So a more natural way to write those kinds of effects is this called conditional effects. So you notice that fly basically says you can do fly as long as rocket is on Earth. And then once you do fly, rocket will be on moon and rocket will no longer be on Earth. By the way, why the heck do I have to say rocket will no longer be on Earth? It looks like a nonsensical thing to say that if it's on moon, why do I have to say it's not on Earth? Yes?
Because then you get used to saying fly action a second time.
No. Why do I have to say rocket has to be, in this particular case, why did I say rocket on the moon and also rocket is not on Earth? Yeah.
To distinguish the moon from as a separate spectrum.
Superposition.
What?
There shouldn't be superposition.
No, it's not.
You have to define that they're like the complementary states.
No.
It's like common sense to us, but as far as like our modeling, if we don't explicitly say that that this action has an effect, the rocket can be on both places.
There was a name I used for it. It's called Scripps assumption. The effect should be complete. It should mention every state variable that is affected, even if it is damn obvious to you. You see what I'm saying? Scripps assumption is the reason why not only do you have to say rocket on moon, but you also have to say rocket is not on Earth. Scripps assumption is also the reason why you had to say not only when you picked up X, not only that X is being held, you have to say it's no longer empty. You have to say hand is no longer empty. You have to say X is not clear. It's very painful. It's pretty obvious to you. Why do you have to say it? But if you say it, then it becomes a much simpler transition function. If not, then you need to actually, the actions are telling you some of the obvious effects. then you need to infer to see what happens to the rest of the fluids. So this is what is called basically given the partial description of the state, then figuring out what should be the values of the rest of the state variables because of the state dynamics. Those are called the synchronic dependencies in probabilistic planning. Okay, and then across states, it's called diachronic dependencies, chronic being that. Okay, so the important thing is the Stips assumption basically requires you to say everything that you're going to touch. That's why you have to say not at all. It's not natural for you to say it. You assume that I should say the obvious thing. We'll be in New York. You don't need to be saying that he would not be, I won't be in Phoenix. Because where else can I be? There are ways around it. For example, you can have things called domain axioms. For example, there could be a domain axiom which says for all x and y at xy implies not at xz. I'm sorry, at xyz. If the x is at y, then it's no longer x. That's a domain axiom. If you have the domain axiom, that's telling you the intrastate dynamics. And then if you say one piece, whatever you know about the state, then you have to complete the rest of the things. But then applying the domain axioms would be theorem proving. For those of you who know introduction to AI, theorem proving is going to be hard. If it, like even for propositional things. Whereas if you do the Stips assumption, then it's very simple to project the states. You see what I'm saying? Okay. The other thing, of course, is the effect is continuous effect, the conditional effect here. It's saying everything that's already in X will be on the moon and won't be on the earth after flying is done. You see what I'm saying? So it turns out these are basically called conditional effects. This is actually syntactic sugar in the sense that it doesn't change the complexity of the planning particularly. It is just makes it even more easy to write the domain models. Because if not, then what will happen is you need to differentiate fly action into like 4 different fly actions. Flying with nothing on, flying with A on, flying with B on, flying with A and B on. You see what I'm saying? And then you will require these conditional effects and become effects. So it's like the plane should take off until Trump is up. And so that becomes a precondition. But normal planes for you and me don't wait for us. If we are in, we get there. If not, again. So conditional effects is a way of dealing with it. Okay. So there is a way of writing this. I mean, I basically wrote this like, reasonable propositional logical representation here as well as here. Here I even threw in for all and for all x, etc. It's even more logic, first order logic representation. But really, there should be some way of writing it down, and PDDL is a particular way of writing it without, basically it's just a syntactic representation for this. By the way, one other thing I have to say is this. Basically, I can, for example, say that I can basically also have a condition. Imagine if you have a conditional effect. Can you possibly have a conditional effect for an action which says X implies not X? I mean, X, if X is true, then not X will be. Do you understand what I'm saying? That's just toggling. And if you think of X and not X as in the same state, such a state is not possible. the thing that you have to remember is in the conditional effects, the antecedent is about the previous state. The consequent is about the next state. So this is not normal logic. If you know the normal logic. So this is essentially saying if X is true in the previous state before the action, then these will be true in the state after the action. There's nothing wrong in saying that. I just removed the state or the situation argument. So it's very important to understand conditional effects essentially are about previous state. The left side is about the previous state, the right side about the next state. And the action sits in the middle. Can you live without knowing all this? Of course you can live without knowing anything. Does it make sense to know this? Yes, if you know this, then you can understand why certain things happen in the way they do in various planning algorithms. Okay. So PDDL is just one representation. There used to be various ways of doing this. Particular for this one, there's a representation which sort of looks like, a way of defining variable, the domain models and the problem as well as the actions. And there's like an example here. So the action operator, the description is in English, just a robot can move from X to Y, and the precondition is room X, room Y, and at robot X at true, and the effect is at Robbie Y becomes true, at Robbie X becomes false, and everything else doesn't change. This is approximately pseudo natural language description. In PDL, it looks like this. That's it. It's just a syntactical representation. And the only reason this is interesting is every planner there's like a class of planning algorithms that can eat this and produce plans. So if you can take your planning problem and put it in this representation, then the algorithm will find it. Okay, now all I was saying was it's so damn hard to go from here to here. For you can put an LLM here and fine tune the heck out so that it will go from here to this. And then you can call the plan. Please don't do that. That's like it's been done first of all, but it's also a dumb way to use LLMs. In the sense, it's a sort of breaking an egg with a sledgehammer, essentially. You don't need GPT-5 to convert some pseudo English to some parentheses, and as much as you might take parentheses. Certainly, you don't deserve a paper for that. But again, there are papers that have been written like this, and they have lots of citations. Some of them are my good friends. That's true though. But that's my friend. Okay. So the first homework is actually going to be released right after this class. Right? And it's basically going to be just you will write a domain specifications using a PDL editor. The editor has a built-in planner too, so that if you write the domain, then it can actually generate a plan and you can see whether or not the domain is correctly specified. One of the problems, of course, is you could write the domain wrong. You have a natural language understanding of what the domain is, and you're writing it in the PDL, and you could have written it wrong. And so your natural language, you think there should be a plan, and then the planner is not finding it. It could be either because the algorithm is bad, because you wrote the bad algorithm, or the algorithm is good, it's taking too long, the search is too big, or the algorithm is good and the problem is small enough, and you didn't find the solution because you wrote this domain model wrong. So in fact, one way of debugging the specifications is to see if whether or not there will be a plan. As weird as it may seem. Right? So that's what you'll wind up doing. So we'll basically give you that. And so there's a PDL editor that you'll figure out. And they will also ask you to give like various types of models and various types of problems written in natural language, and you want to convert it into PDL. So one idea would be actually, so by the way, one of the funny things about the thing that I was making fun of earlier was actually when I was talking about you could go from here to here with LLMs, actually the papers that are written basically assume that the planner and the PDL model for the blocks world already exists. And the goal and the initial state is given by you in English. and they just convert ing into parenthetical, not the domain model. Do you understand what I'm saying? So everything else is ready. It's just that the goal, basically, and the initial state, you wrote it in English, and the LLM converts it into PDL form, and then you give it to the planner and it produces. That's a paper. Okay. Now, a more interesting thing you can ask is, once you do this example, you will realize that actually writing domain models is not all that fun. This is going to be a simple enough thing, but in general, for a complex enough domain, you need to understand, you need to figure out how to write it, what are the preconditions and effects. It's not the syntax part that is hard. It is just sort of conceptualizing the domain in terms of what should be the actions, what should be the preconditions, what should be the effects. That's going to be painful. So there is actually, in planning, in the classical planning world, in the planning domains, people assume somebody already wrote the domain. That's called the knowledge acquisition aspect. So somebody sat down and wrote the domain in the PDDL, and they only focus on the search part. But writing the domain is not a simple thing. You see what I'm saying? In a weird way, notice that writing the domain is writing the model. You want to learn models, or you are expecting people to give you the models? You're expecting the people to give you the models in a compact form. That's exactly what writing the domain is. Right? And so that you can just depend on the inference, focus on the inference. One thing that if you already have LLMs, one thing that you actually can have LLMs do for you is you can ask the LLM, pre-trained LLM, I have this kind of a box word, what do you think should be the actions? What do you think should be the effects? What do you think should be the preconditions? And he'll give you some conceptual formulation. Then you can check if it is correct or not. So just like you have a program specification in software engineering, rather than write your own code, you ask Claude, do the needful. And basically Claude will write some stuff. If you're lucky, it will work. If not, you have to still correct. You understand what I'm saying? This is a reasonable thing for LLMs to do. I'm saying partly because we wrote a paper on it, so it must be simple. But more interestingly, it's actually using LLMs for what they're actually good at, which is they have the knowledge of all sorts of things, sort of approximately inbuilt. And you can just basically ask it question by question, what are the actions for the people, etc. And that could potentially reduce the domain modeling problem. And there's a paper actually in 2023 by a guy called Nguyen, one of my students, and then Karthik Valmikam, which basically shows that you can use LLMs to actually extract domain models. But you will get a domain model. Just as, remember what I said about LLMs, they will never say no. If you ask them anything, what's the meaning of life, they will tell you something. There's no such thing as I don't know. If you ask a domain model, it'll tell you a domain model. If you ask what are the actions, it'll give you some actions. What are the preconditions, it'll give you some preconditions. And it's again that ordering order. The question then is, then you can essentially be in the loop and try to reduce the amount of work you are doing. Okay, so this paper that you can read, I might make you read at some point of time, but I'll try to at least put you a link to it. This NUNIPS 2023 paper basically tells you how you could have extracted the domain models from it. Notice that you have to compare this to, if you're talking about model learning, right? You could have a large number of traces of the agent going from state to action to state action state traces. And you're going from those traces to a kind of a PDL model or some transition model. Here, you're just directly asking the LLM because it has some common sense knowledge about all sorts of things, and then it might suggest what might be the preconditions. It's not going to be guaranteed, but then you will still have to be involved in. This is actually, we'll talk about, there are ways in which you may have to verify. So one of the things that actually happens in doing Claude code art, etc., basically is that when you have code, typically, if you especially care about the correctness of the code, you will give these unit tests. If the code works, these unit tests must have the following values. Right? And what you can then do is if Claude produces, Claude or GPT-5 or whatever, produces a piece of Python code, there is a Python interpreter. But whatever the heck that guy's name is has written. What's his name of the Python guy? Wait, what? The guy who came up, what? Yes, not what? Say it again. Guido guy. Guido guy wrote. Thanks to Guido, we have a Python interpreter. And we are extending it. Okay. It's not LLM, it's Python interpreter. If you ever write anything that's in Python syntactically, Python interpreter can run it. That's not a normal thing. It's pretty impressive that Python interpreter can interpret anything that is in the syntactic Python form. Python interpreter can't write, simulate or interpret some nice Shakespearean, iambic pentameters on it. But it can interpret any arbitrary looking Python code. And so for every unit test, you have the interpreter, you have the guest code, you give the unit test to the code, unit test on the code to the interpreter, it tells you what comes out. You check if that's what it's supposed to come out. If it's correct, then you know that it must be correct. Modulo these unit tests. Here you are using Python interpreter as a verifier along with the unit test of the code that LLM generated. Do you understand what I'm saying? So later on we talk about some of our work and also other people who are generally interested in this called LLM modulo. An LLM modular approach in general is let LLM guess the solution in a syntactically valid form and have a verifier that checks if the solution is correct. And the verifier is not LLM, it is an outside verifier. So if you actually only know how to check if a plan is correct or not, and you don't want to have to generate the plan. So you can actually check the correctness of the plan with respect to the verifier, let the LLM guess the plan. And this is what's called a generate test paradigm. You generate, you test. Normal generate test is the dumbest idea possible because the generator can generate all sorts of crazy ideas. Most of the time, the tester will say wrong, 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 wrong. You see what I'm saying? A way of thinking about it is imagine there is a Shakespearean verifier, which basically takes some text and says, is this Shakespeare? Quality. And you have infinite number of monkeys typing away at the typewriter. It's theoretically possible that they will produce Shakespeare. It's also theoretically possible that it will take as long as it probably doesn't happen before the universe ends and the next ice age begins. That's why generate test is a dumb idea generally. But if there's one good thing about LLMs, they are good generators. They're actually better plausible generators than just randomly guessing some arbitrary. You can say they're hallucinating. Yes, they do. But man, the whole point that you're saying is hallucinating is that some of the time they're actually right. So you're surprised enough that sometimes they're wrong. Whereas you never say infinite monkeys are hallucinating. Right? They're basically writing gobbledygook all the time. You understand what I'm saying? So given that view of LLMs, then LLM modulo systems essentially say, let the LLM be the guesser and have a verifier or a partial verifier in them. And if you think in those terms, you can actually do LLM modulo for planning. We will talk about it later on. But you can also do it for domain model construction. Think of domain model as a Python program. Unit test will be some number of planning problems and their correct solutions. Python interpreter is the plan, the PDDL plan. You let the guy come up with a domain model and you can actually check, in fact, if the unit tests are. And you can do something in between. In fact, here you can do partial validation. In fact, it turns out that these things called val equivalent to Python interpreter. There are things like val system, which is basically takes any plan in the PDL format and checks if it is correct with respect to a domain. So this is not just a high level analogy, it actually works. So it turns out in this particular case, we are talking about how do we actually just get the domain model. There's just way too many black boxes here, but I'm just saying this is one way you can use LLMs to actually get your PDL model if you want that. Okay. Yeah, so there's some results on that too. So one other thing before, let's see, there are a couple of things I could do. Let's see, actually, I'll skip over this. Actually, let me just do this too. So imagine, one of the things I'll get back to, and I'll actually spend an entire lecture and then make you read papers too, is given all this, if I just give the domain the problem specification to the LLMs, can they not just come up with the correct plans? Just write out, right? That's a reasonable thing. And in fact, it turns out there are lots and lots of papers that are written saying LLMs are zero-shot planners. And so one of the interesting questions is, will they do for this very bad kind of Bloxworld, kind of simple Bloxworld problems? And one of the things we'll see, and we'll talk about it later more, thing is that actually, if you talk about standard LLMs, at the time when people were making these statements that they can generate all sorts of plans, very costly plans, very impressive plans like wedding plans, travel plans, etc., they could generate 4 Bloxworld plans. In the sense, the Bloxworld plans that they generate would be intact. They can either be not executed, or even if you execute, they won't reach them, as checked by the verifier. So it turned out that even at the time when people were assuming, it turns out all these other guys, Claude 3, Opal, GPT-4, GPT-4. This one actually is much later. Actually, we started GPT-3 and GPT 3.5 timeframe. They're all much worse in terms of their accuracy. And as the models became better, then they kind of increased performance, like 40.1. Again, remember, there's just so many models coming up. This is, I don't remember when, this is 2024 results. Okay. One of the interesting questions is, there seems to be some kind of an improvement, at least in the same family, as you go from the bigger numbers, GPT-3 to GPT-4, etc. So the question is, have they figured out how to do that? One idea that you actually have to consider is, are there alternate explanations as to why they are doing better? With LLMs, the alternate explanations are there's a lot more training data. Between GPT-3 and GPT-4, there's more training data. And what if they actually got trained on more Bloxworld problems? Do you understand what I'm saying? And that could also explain. So, for example, if a kid has failed in the beginning about the why are manhole covers round question and didn't get into interview, and then their juniors who came 1 year later were passing left and right with this question, is that because they're smarter, or is it because they got the question back and not bigger? Do you understand what I'm saying? So how would you show that when something solves a reasoning problem, that it might actually have memorized that? How would you show? It's easy if you can actually tell the training data. You look at the training data. But for LLMs, it's impossible to look at the training data because the entire universe of anything on the web is the training data. Okay, so what you will need to do is these ideas of diagonalization, which is doing things such as one of the things that we'll show here. Yeah. So this is Bloxworld problem. And I wrote in the pseudo English. You can read this. This is mystery Bloxworld. All I did essentially was, instead of picking up, I'm saying attack. Instead of block, I'm saying object. Instead of unstacking a block from another block, I'm saying feasting an object onto other object. Okay? And instead of put down a block, succumb an object. Stack a block, overcome an object. It turns out this is painful for you because you try to make sense of the English word. But do you think the planners actually don't care about the English words? It turns out you can write this as a PDDL model, and you can write this as a PDDL model. They are essentially isomorphic PDDL models. And planners, any planner that solves this will solve this with exactly the same amount of compute. No more, no less. Do you understand this? In fact, you should definitely understand this in this class. And in fact, that's what I was saying, that a block by any other name would stack as strong, as Shakespeare said, a rose by any other name would smell just as sweet. Changing names doesn't change the dynamics. Right? So if in fact if you know how to solve the problem, then the name shouldn't matter. You may get a little confused, but you will be able to solve. And what we find is this mystery domain. If you look back to the previous case, this is the mystery blocks world, and those numbers suck. You understand what I'm saying? Those numbers suck. That's a way you know that at least standard LLMs, this is not reasoning models, these are standard LLMs. They're doing some kind of memorization. It's not surprising to you. I mean, you probably saw on the Twitter a large number of these cases, like for example, the farmer goat problem. When you remove some of the constraints, you still come up with the costlier solution. Even if you have no wolf, it will still make three cubes. It's unnecessary, but it knows how, the only way it knows how to solve this. Okay, so we showed this. The interesting thing that other people don't understand, but you will understand in this class, is this guy. Is Drew McDermott. Ask away. Very smart guy. There are multiple reasons you should know Drew McDermott. One of which is that he wrote this very beautiful paper called Artificial Intelligence Meets Natural Stupidity in 1977. And it's kind of required reading for anybody in AI. Because the problem with AI is that you always anthropomorphize. And in fact, next Tuesday, I'm giving a talk about anthropomorphization sins on modern AI, or why you don't want to put a lens of cognition on LLMs too prematurely, because that typically throws you off the right track as to why actually the models are. That's one thing he did. The other thing he did, he was actually a planning guy, and he came up with the PDDL standard. It was a list buff, which is the reason why you got stuck with this stupid pens. And a third thing from this particular planning thing, oh my God, I forgot. I remember this domain independent, domain specific, etc. stuff. There was a planning competition in 1998 onwards. We started having international planning competition in this planning conference to see whose algorithms are able to solve planning problems fastest with accurate solutions. And for some reason, once you become a competition, people basically would wonder, what if it is a planning competition for domain independent planners? But what if you know that there are only like 5 or 6 words in the benchmark, right? Blocks word is one, logistics is another, something else is another, and you write a piece of code which is binary, and then there's a big case statement inside, which says, if it says pick up, go to the box word. If it says, truck, go to the logistics word. And in each of those cases, you have a domain specific plan. And the domain specific plan is pretty much faster, right? Because you actually compile them to be very efficient for just that code. The whole point of domain independent is you're only given the domain at the time of the competition, and you still should be able to do that. So Drew was worried, how do I catch people like that? And believe it or not, there actually were people who did this. You do competition, people will find a way to cheat. Benchmarks will always be cheated. Competition will always be cheated, because that's what we do. Right? So it turns out actually there was actually a particular group which did almost exactly what I said. They went into that binary and found out that they had a big case statement. If it starts with block, do this. If it starts with truck, do this, etc. And so what he did was he did this mystery thing where he changed the names. And to catch people who might be doing this. This is a diagonalization argument. And now Interestingly, we did the same thing for LLMs, the same idea, but for LLMs, because LLMs probably would not have seen this kind of a domain. They're more likely to have seen this kind of a domain. Not because they're cheating, but because that's the kind of domain that was there on the web. There's lots and lots of stuff about lots and lots of stuff about logistics, lots and lots of common sense. So it turns out you can also do, by the way, instead of these, you can also do attack and object, etc. You can do random strings. That is, for every predicate or object name, you have a specific random string and you global replace. You'll get a new model. And you have to understand that logically the two are exactly the same, even though you can't make sense of it. You understand what I'm saying? I mean, after all, you write, generate programs with comments, etc., etc. When it goes to the computer, it's a bunch of instructions. They don't look like anything that you can make sense of. But it works. Right? So ultimately, the important thing is that a domain, if you change it like this, then essentially that's a way of capturing whether things memorize or not. And in fact, we find that all standard models, all the way up to GPT 4.2, etc., just died on history books. Reasoning models do improve, and I'll explain to you why they actually improve later on as that goes to. Okay, but notice the nice connection between what was done for catching the culprits in the planning competitions and what is done to catch LLMs in action. There's nothing wrong. It's just all I'm saying is you are legally, and so maybe you will not be able to do it right if I change the specification a bit. You see what I'm saying? Okay. I think I'm almost done. So that is about, and so we already talked about why are the PDL models more compact. You understood that, I hope. There's strips assumption is an important thing you need to understand. One of the things you also need to understand is in the models, effects cannot have disjunction. Effects cannot have disjunction. Because if an effect has disjunction, that means it's not a deterministic action.
Yeah.
It's a stochastic action. Preconditions, on the other hand, can have disjunction. That means either this is true or that is true. That's okay. Effects cannot have disjunction. Do you understand what I just said? Okay, and this is actually one of the reasons why it's actually important to know what I just said earlier. If in fact you have an action A which says E1 implies E2 as a conditional effect, and you're a smart undergrad student who has taken logic course and you know E1 implies E2 is nothing but what? A implies B can be written as what? Not A or B, right? So if I have this, why can't I write this as A, not E1 or E2? If I write this, then I'm allowing distinctive effects. But I said distinctive effects cannot be possible. But I also said conditional effects are okay. What gives? Because E1 is not in the same state as E2. E1 is in the previous state, E2 is in the next state. Which is why this problem is. Do you understand what I'm saying? So that implication there is not classical implication. It is really the state variable is missing. You know, if E1 is true in the previous state, then E2 will be true in the later state. So if you convert that into with logic rules, then it says not E1 in the previous state or E2 in the next state, which is wrong, which is not wrong. Do you see what I'm saying? Okay. And then typically, if you do have quantification, those quantifications are over finite universes. So that means, like, for example, there was for all x in x implies at x moon and not at x earth. That would be a finite, it has to be a finite universe, for PDDL, you know. And then you can compile down the actions into a canonical representation that removes the conditional effects, but that blows up the number of actions. I told you this, right? For example, instead of just having one fly action with conditional effects saying anything inside will get to the moon, you need to have one fly action with nothing inside one fly action with A inside, one fly action with B inside, one fly action with AB inside. So if there are two objects, there is 2 power 2 actions now. If there are n objects, then you have 2 power n. That's the compilation that will happen. So, it becomes more baroque in terms of the country. That's what we're thinking about. One last thing. And as I said, there is some psychological validity strip style action models. People have looked at how we think. I mean, probably you kind of realize that actions, you think of actions as what needs to be true before the action and what needs to be true after the action. Yeah. And then there's this stuff I would not deal with right now, but essentially if you compile it, then one of the advantages is you can write in conditional effect model, compile it away to normal classical scripts, then there are more planners that work on the classical scripts. If you have conditional effects representation, there are fewer planners that know how to directly deal with condition. It's just a question of algorithm issue. Okay, so there is this reduced instruction set kind of issue. Since we can do the stuff doing compilation beforehand, and you can actually use the same planners. And then a lot of people actually, one of the things that in the classical planning domain, what people did is they take more and more kinds of planning problems, somehow convert it into a kind of a strip stack planning problem so that you can solve it with the same solver. Maybe instead of solving one, you will solve like exponential number. So this is what is called compiling more complex problems into classical planning. This is more from the planning perspective. Yeah. So obviously you won't have any questions right now. I'll say you can have questions next week. But when we come back, why the heck am I not getting here? Why is it not showing this? Yeah, that's going to be the next class's agenda. Just to give you, that's kind of the second part of the chapter. We'll talk about progression, regression, and plan space planning, which is if you give a plan, how do you check if the plan is correct? You should check it in one way, which is do the first action in the first state, you get a new state, then do the next action, you get a new state, you do the third action, and then you add to the end, and then check if the goals are present in the plan state. If so, that's a progression proof. You can do the regression proof, which is you start from the back and go towards the front and see the stuff that you're expecting is a subset of the wishes. You can do a completely different idea called plan space planning, which sort of hinted last time, which is work on supporting everything with an action that gives it recursively. That means if you need A, somebody should be supporting A. And if that somebody needs B, then somebody else should be supporting B. Then. And then anybody is supporting something for a different condition in a different time point, they have to come before it. But doesn't have to come immediately before, it just has to come before something. And then in the interval between where you are giving and somebody is taking, nobody should come and delete that condition. That's what's called plan space plan. So for each of these, there are 3 different ways of checking if a plan is correct. And for every way of checking if a plan is correct, you invert it, you get a search. Progression search, regression search, plan space. And more interestingly, if you know any one way of checking the correctness with respect of a plan with respect to any of these approaches, right? A correct plan will be correct for all these approaches. Right? There are 3 different ways of proving the correctness. Irrespective of the way you check the correctness of the plan, if you have one, then you can actually use it in this verifier loop, LLM modulo kind of a loop, with that as the verifier and LLM guessing plans more. Yes.
When you say correct plan, do you mean like valid plans at the same time?
Yeah, so what I mean is essentially it's like it executes and it reaches the goal. That's what it is. So validity, I mean, there are different ways people define these things. When I say correct, that means it should be executing and it should get to a state where the goals are set. And so next class, what we'll do is we'll talk about 3 ways of proving the correctness of plans in this very simple strips representation. And then talk about how they get converted into search. That's a lot more like intro to here. And then from the perspective of LLMs, then any way of checking the correctness, any one way is enough. You can do this. Generate test. Let the LLM generate and you test and then you send back. Say like That's where we'll go. And so we'll spend some of the time also understanding next class about what makes planning problems hard versus easy. And one of the things is connected to these interactions between actions. I mentioned it, but I can actually talk about it completely in terms of these kinds of actions. We talk about independent subgoals versus positive interaction subgoals versus negative interaction subgoals. Independent subgoals means you can generate plans for each of the subgoals separately and just mix them in any which way it will be correct. That's the place where LLMs are extremely good. Positive interactions basically means doing progress on one subgoal actually helps the other subgoal. So the overall plan can be shorter than the plans for each of the subgoals combined. Negative interactions means doing progress on one subgoal actually violates the progress on the other subgoal. So for example, A and not A can be a goal state. You can have a plan for A, you can have a plan for not A. There is no way of combining such that A and not A will both be true. And it's when the negative interactions exist is when you need the search. And that's where LLMs actually find out failing. And most of what the planning algorithms do is how to deal with those people. Okay, thank you.